All right, so today we're going deep inside computers,
Really deep.
like way down into how they actually execute the instructions that we give them.
And not just that, but also how they handle getting information in and sending information out.
Exactly like input and output. You know, like when you click a mouse
Yeah.
or type on a keyboard.
Yeah, all that stuff, like when you open an app or save a file.
It's like getting a backstage pass to see the magic happen.
Right, all that behind-the-scenes stuff that
Yeah.
makes computers work.
So let's start with the basics, the foundation of it all, the instruction cycle.
The heartbeat of a computer.
Yeah, like the process it goes through for every single instruction it has to carry out.
Every single one.
So can you walk us through that? Like, what are the steps involved?
Well, imagine a computer as a really efficient chef
Okay.
who's following a recipe very carefully.
All right. I like where this is going.
So every line of code in a program is like a step in that recipe.
Makes sense.
And the instruction cycle is the chef's process of reading each step, carefully gathering all the ingredients, and then executing the instructions perfectly.
That's a great analogy.
Yeah.
So what are those key phases in that recipe or, I guess, instruction cycle?
Well, there's 6 main phases.
6.
Yeah. So first up, we have fetch, which is where the computer grabs the next instruction from memory.
Okay, so it's like the chef picking up the recipe book.
Yeah, and then looking at the next line.
Got it.
Then comes decode,
Okay.
where the computer figures out what that instruction actually means.
So like what needs to be done.
Exactly, like what operation needs to be performed, what data is needed.
So it's like the chef understanding, do they need to chop or saute or whisk?
Precisely.
So it's not just blindly following steps.
Real.
It's understanding what each one means.
Right.
Okay, so what's next?
And we have evaluate address.
Evaluate address.
Yeah, where the computer figures out where the data for that instruction is stored.
So like where are the ingredients?
Exactly. It's like the chef locating the specific ingredients they need for that particular step.
Okay, so we're finding the location of the ingredients in our computer's pantry.
Yeah, think of it that way. And then comes operand fetch.
Operand fetch. What is that?
So that's where the actual data needed for the instruction is retrieved from memory.
So now we're actually grabbing the ingredients off the shelves.
Exactly.
So we've got the instruction decoded and the ingredients ready.
Right, time to cook.
Let's do it.
So the next phase is execute, which is where the magic happens.
Ooh, the main event.
Yeah, this is where the computer's processor actually performs the operation that was specified in the instruction.
So our chef is combining all those ingredients, maybe applying some heat, and creating something delicious.
Precisely.
And finally, we get to enjoy the results.
Yes, the last phase is store result,
Okay.
where the outcome of that operation is saved back into memory.
So like the chef placing that finished dish on the counter.
Yeah, you got it.
So this entire cycle, this whole process repeats for every single instruction.
Every single one.
And it's happening at like blazing fast speeds.
Oh, yeah. Millions or even billions of times per second.
That's incredible. It's just mind-blowing to think about all these steps happening behind the scenes every time we do anything on our computers.
It is pretty amazing.
So let's dive into a specific example to make this a bit more concrete. Can we walk through how adding 2 numbers would go through this entire cycle?
Sure, absolutely.
Let's say we want to add 13 and -5 using our computer.
Okay, 13 and -5. So the ADD instruction is the star of this show.
All right, the ADD instruction.
So imagine the computer's data path, which is basically the pathways that data flows along as our kitchen from before.
Okay, I'm picturing it.
So first step, we fetch the ADD instruction from memory, like grabbing that recipe card for
Actually, I
adding.
have the recipe card.
Then during the decode phase, the computer realizes, okay, this is an ADD operation. I need 2 numbers to work with.
Gotcha. So it knows it needs 2 ingredients.
Right during the evaluative address and operand fetch phases, it locates and retrieves those numbers 13 and -5 from registers.
Registers.
Yeah, registers are like little storage compartments within the processor that hold data that's being actively used.
Okay, so it's like grabbing those pre-measured ingredients from the fridge.
Exactly. Now it's time for the ALU to shine.
ALU.
The arithmetic logic unit, think of it as a super fast calculator that's built into the processor.
Okay, the computer's calculator.
Right, so during the execute phase, the ALU adds those numbers 13 and -5.
And we get 8.
And during the store result phase, that sum, that 8, is saved back into a register.
Okay, ready for the next step.
Exactly.
Now here's something I find fascinating. The computer isn't actually dealing with the numbers 13 and -5 as we see them.
Right.
It's all happening in binary.
You're right, it's all ones and zeros.
The language of computers.
Yeah, the computer's actually working with the binary representation of those numbers. So 01101 for 13 and 1011 for -5. But the cool thing is that the instruction cycle hides all that complexity.
That's a good thing.
It lets us interact with computers using these familiar concepts like adding numbers.
Like magic.
Yeah, in a way.
So we've seen how the computer follows that recipe book really carefully, executing each instruction step by step. But now let's move beyond the kitchen.
Okay.
And talk about how the computer talks to the outside world through input and output.
I/O.
I/O. What's the story there?
Well, just like our chef might need to get more ingredients or, share that finished dish, our computer needs to interact with the outside world too. And that's where I/O comes in.
It's like the doors and windows of our computer kitchen, letting those ingredients in and those delicious digital dishes out.
I like that analogy, and the way the LC3 computer handles I/O is really interesting.
LC3?
Yeah, it uses a concept called memory mapped I/O.
Memory mapped I/O.
So basically think of it like the special memory locations are designated as doors to these I/O devices, like the keyboard or the display.
So these memory locations aren't actually storing data like regular memory?
Not in the traditional sense, no. They're more like communication portals.
Oh, interesting.
So reading from these locations is like receiving input, like a key press on the keyboard, and writing to them sends output, like displaying a character on the screen.
I see. Can you give us an example of how this works in practice?
Sure. Let's say you type the letter A on your keyboard.
Okay.
When you press that A key, the keyboard sends the ASCII code for A.
ASCII code?
Yeah, which is 01000001 in binary.
More binary.
It sends that code to the designated keyboard input location in memory.
Okay, so the code for A arrives at the computer's doorstep.
You could say that, and then the computer can read this code from memory and use it in a program.
So it might display it on the screen.
Exactly. And to display A, the program would write its ASCII code to the designated display output location.
So it's all about these specific codes being sent and received through these special memory locations.
Right. And that's how the computer translates our actions into something it can actually understand and work with.
This is all so fascinating. We've taken this journey through all the steps of the instruction cycle, and now we're seeing how the computer connects with us and the devices we use.
It's all connected.
But there's so much more to explore. What's one key takeaway you want our listeners to consider as we wrap up this part of our deep dive?
Well, I think the key takeaway is that these fundamental building blocks,
Instruction cycles and I/O.
yes, they form the foundation for everything your computer does.
It's amazing to think that something as simple as adding two numbers can involve so many steps, and it makes you appreciate the complexity of things like opening a file or streaming a video.
Absolutely. And while those actions seem way more complex, they're still built upon those same basic principles of instruction cycles and I/O.
So even something as intricate as streaming a video is really just a carefully choreographed sequence of fetching, decoding, and executing instructions.
That's exactly right. Of course, the instructions themselves are more sophisticated than just adding numbers. They involve interacting with different parts of the computer's memory, managing data storage, and coordinating with various hardware components.
So it's like our chef now has a whole team of sous chefs, each specializing in a different culinary technique, and they're all working together to create this really elaborate feast.
That's a great analogy. Take streaming a video, for instance.
Yeah.
It requires fetching data from the internet, decoding compressed video and audio streams, and then sending those decoded signals to your screen and speakers.
Wow, and all happening in perfect synchronization.
Right, that sounds like a ton of instructions being processed really quickly.
It does, and yet it all seems so effortless from our perspective.
It's a testament to the efficiency of the instruction cycle. It's humming along at an incredible pace, handling all these complex tasks with remarkable efficiency.
So we've got the big picture now, but I'd love to understand some of the finer details of I/O on the LC3. For example, how does a computer know where to find those special memory locations that act as doors to the I/O devices?
That's a great question. So the LC3 uses a fixed set of memory addresses for these I/O devices. For instance, the keyboard data register, which we can call KBDR, is located at a specific memory address XFE02.
XFE02.
Yeah, so whenever the computer needs to check for a key press, it just looks at the contents of that specific memory address.
Well, so if a key has been pressed, the ASCII code for that key will be present in the KBDR.
Exactly.
It's so simple. It's so elegant.
Yeah.
What about output? How does the computer send data to, let's say, the display?
So the display data register, which we'll call DDR, is responsible for that.
It's DDR.
Yeah, and it resides at memory address XFE04.
XFE04.
So when the computer writes a character's ASCII code to this address, the character pops up on the display.
I see. So these fixed addresses act like dedicated communication lines between the CPU and the I/O devices.
Right.
But if the addresses are fixed, how does the computer know when it's accessing regular memory versus performing an I/O operation.
That's where the control unit comes in. It's the brains of the operation, you could say.
Okay, the control unit.
It knows which memory addresses are assigned to I/O devices and issues the right commands for reading from or writing to those devices.
So it's like the control unit has a map of the computer's memory and knows which areas are for data storage and which are for those I/O operations.
Exactly. It acts like a traffic controller, making sure data flows smoothly and correctly within the computer.
This actually connects back to our discussion about the instruction cycle.
How so?
Well, ultimately, I/O operations are just another type of instruction for the computer to execute, right?
You're absolutely right. Whether it's adding numbers, accessing memory, or interacting with these I/O devices, it all boils down to that same fundamental process. Fetch, decode, evaluate, address, operand, fetch, execute, and store result.
This deep dive is really shedding light on the inner workings of computers. It's amazing how a seemingly simple model like the LC3 can provide such a clear understanding of these concepts.
It really does. And before we wrap up this part, I think it's worth highlighting the elegance of memory-mapped I/O. It's a really efficient approach.
I'm curious about that. What are the advantages?
Well, the beauty of it is that it simplifies both the hardware and the software design. Since I/O devices share the same address space as regular memory, the CPU can use the same instructions for both data access and I/O operations.
So there's no need for specialized I/O instructions.
Exactly. It streamlines the instruction set and makes the control unit's job easier.
That's clever.
Plus, it makes the system more flexible. You can add new I/O devices just by mapping them to available memory addresses.
I'm starting to understand why the LC3 is so popular for teaching computer architecture. It's a simplified model, but it really captures the essence of how real computers work.
It's a fantastic foundation for understanding the fundamentals, and once you understand these concepts in the context of the LC3, it's much easier to appreciate the complexities and advancements of modern computer systems.
Will said, this exploration of instruction cycles and I/O on the LC3 has been truly enlightening. But we're not done yet. Stay tuned as we delve into even more fascinating aspects of I/O in the final part of this deep dive. Welcome back to our deep dive. We've been exploring the fascinating world of instruction cycles and I/O.
And how they work together to make computers do all the amazing things they do.
But one thing that's been on my mind is the issue of speed. Like, the CPU can process instructions so incredibly fast.
Oh yeah, blazing fast.
But I/O devices like keyboards and displays tend to be much slower. How does the computer handle that difference?
That's a really important consideration in computer design. You wouldn't want the CPU, which can execute millions of instructions per second, to be held back by something like a keyboard.
Right. It'd be like a master chef waiting for the oven to preheat for hours before they could start cooking.
Exactly. Not very efficient at all. That's where interrupts come in.
Interrupts?
Yeah. Interrupts allow I/O devices to signal the CPU when they're ready to send or receive data.
So it's like the oven sending a notification when it reaches the right temperature.
Perfect analogy. The chef doesn't have to keep checking the oven. They can focus on other tasks and just go to the oven when it's actually ready.
I like that. So in the LC3, how does that actually work?
Well, each I/O device has a special bit in its status register called the ready bit.
The ready bit.
When the device is ready for an I/O operation, it sets that ready bit to 1.
Okay, so it's like the oven's notification system.
Right, but how does the CPU actually know to check for these notifications?
That's what I'm wondering.
So the CPU regularly checks a dedicated line called the interrupt request line.
Interrupt request line.
Yeah, and this line connects all the I/O devices to the CPU.
Okay.
So if any device has set its ready bit and is requesting an interrupt, the CPU will detect a signal on that line.
So it's like a central alarm system, letting the CPU know that something needs attention.
Exactly. And when the CPU receives that interrupt request, it puts its current task on hold, saves its progress, and jumps to a special program called an interrupt service routine.
Interrupt service routine. So it's like the chef putting down their current task and going to check on the oven when they hear the notification.
Precisely. And the interrupt service routine handles the specific I/O operation that was requested.
Okay.
For example, if the interrupt came from the keyboard, the routine would read the character from the KBDR and store it in memory.
And once that I/O operation is complete, what happens next?
The interrupt service routine returns control back to the CPU, which then picks up where it left off.
So it's like the chef going back to the recipe.
Right. It's a very clever way to keep things running smoothly. The CPU doesn't waste time waiting for those slower I/O devices, but it can still respond quickly when they need attention.
I'm starting to see how essential interrupts are for efficient I/O operation.
They're absolutely crucial.
But I'm curious how this all connects to the software we use every day. Do interrupts have any impact on our user experience?
Oh, they play a huge role in making our computers feel responsive and intuitive. For example, when you're typing interrupts, ensure that every single keystroke is registered right away, even if the CPU is busy doing other things.
So that's why our typing feels seamless and our computers don't freeze up every time we interact with a device.
Exactly. They're working tirelessly behind the scenes to manage that flow of information between the CPU and the outside world.
This entire deep dive has been so eye-opening. We started with a simple analogy of a chef following a recipe, and now we've explored all this complexity with instruction cycles, memory-mapped I/O, and interrupts.
It's amazing how all these actions we take for granted on our computers, like browsing the web, playing games, or just typing a document, all come down to these fundamental concepts.
And the most remarkable thing is that all these complex mechanisms are designed to make our interactions with computers feel so simple and effortless.
It's a real testament to the ingenuity of the computer scientists and engineers who created all this.
Well, this has been a fantastic journey into the heart of computer systems, and we hope you've enjoyed this deep dive as much as we have. Until next time, keep exploring and keep asking questions.